So you need to add up the total amount of beads first,
Yep.
which is 12, so be out of 12.
Okay.
So if both beads are green, would it be 2 out of 12? Wait, no. Would it be 2 out of 12?
7 green, 5 blue. What is the probability of taking a green the first time?
What is 7 out of 12?
7 out of 12. Probability of taking it second time.
It's half that.
Oh, how many greens are left?
5.
After you've taken it the first one?
6.
How many total now?
11.
That's it. That's how you do it.
Okay.
And yeah, okay. When you're ready, B as well.
So for A, would it be 7 over 22 or 0.312?
I like 7 over 22.
So for B, would you need to do 7 over 12 times 5 over 12?
How did you get 5 over 12?
From the blue beads. 5 blue beads.
Okay. There were 12. But you took one out. So it's 7 over 12 times 5 over
11.
Yep. That's alright, what is that one?
35 over 100. 35 over 132.
Okay. There is another possibility.
Is it 7 over 11 times 5 over 12?
Yeah, you could get them the other way around. So 5 over 12 times 7 over 11. It's basically probability of blue than green.
Yeah.
And you'll notice something.
Which is 35 over 132.
Yeah. It's basically you've got double your chances. And so, what is the probability of getting 2 beads of different colors?
You multiply it by 2.
Yeah, or like that's the same as adding these two together. And
which is 35 over 66.
So that is 35 over 66. Yep, great. 35 over 66. So they did a diagram for it. Diagram is helpful, especially as they get more complicated.
Yeah.
All right, let's try this one.
So would there be 2 lines, one leading to motorway and one leading not going to the motorway?
So yeah, we could do it. Let's go down here. So this one is motorway. This one is not motorway.
And then for motorway it'd be 0.4.
Mm-hmm.
And then there'd be 2 lines coming off motorway.
Okay.
And it'll be on time and not on time.
So that's on time. That's not on time.
And for on time it'd be 0.9. And then from not motorway you'd have 2 lines as well, and on time and not on time.
Mm-hmm.
And then on time is 0.3.
Okay. Yep.
Okay.
You've got some blanks.
Yeah. So for this, how do you work out like the one that's not on time on the top?
What the probabilities add up to?
1.
Yep. So this 0.4 is motorway, so not motorway.
Oh, would be 0.6.
Yep.
So the other one would be 0.1 and the other one would be 0.7.
Mm-hmm.
And then would you do you'd put add at the end and then like you'd add them and then equal each of like numbers,
No.
each line.
No. Done. Part B.
Okay. Are they independent?
Takes more to rise in time are independent. If you remember, probability of motorway. Do you remember what's true if they're independent?
No.
Probability of motorway times probability of on time is equal to probability of both.
Okay. So you times them both together.
Yeah. What is the probability of the motorway?
0.4. Well, like 4 out of... No.
0.4 is fine.
0.4.
What is the probability of both motorway and on time?
You times it by 0.9.
So that's 0.4 times 0.9.
Which is 0.36.
Okay. But the probability of on time, how do we get that?
But it says it there, doesn't it?
Well, there's two possibilities. It is the probability, it's like 0.4 times 0.9. Yeah.
Mm-hmm.
It's also 0.6 times 0.3. There's two different ways that you can be on time.
Oh, okay.
And so work out that bracket in there and see what it is.
The bracket it would be 0.54.
Okay. I don't think that's going to work out. What do you get when you do that one?
You get, if you times it by 0.5,
Mm-hmm.
you get 0.27.
0.4 times 0.5? This whole thing was 0.5?
Yeah,
Okay.
I think. Wait, let me double check.
No, I think you're right.
Yeah, it's 0.54, and then you times it by 0.4.
Yeah.
Which gives you 0.216.
216, which is not 0.36.
Yeah.
Therefore,
It's not independent.
that's it. And part C.
Okay. It is 0.46.
And how'd you get that?
I worked out by multiplying them together and then adding them. But
So-
I realized that you can like take away from 1 0.54 to get 0.46.
Okay. Yeah, that's a good point. I didn't think of that. 0.46. Now, probability time is different for each of the two initial choices. Oh, that's even quicker. Part B. So the probability that you're on time, if it was the same for both of them, then it would be independent. It wouldn't make any difference. Motorway, not motorway. The probability that you're on time is the same.
Yeah.
So that's part of the benefit of tree diagrams. You don't have to do the multiplying like you do with Venn diagrams.
Yeah.
Okay. Draw a tree diagram. I think you're okay for... Alright. I'll do one. Draw a tree diagram for this. You'll just complete my tree diagram.
Okay.
Plays golf. Par or under of the
So
first
there'll
hole.
be 2 lines, and 0.7 will be on one line, which is par. And then the other one will be 0.3, which is under.
Yeah, that's the main thing. I think that's not par. If he scores par.
Oh, okay.
And if he doesn't score par on the first hole, the probability scores. So that's 0.4, is it? So,
Yeah.
so that must be 0.6. That must be... If he doesn't score par on the...
I think it's
this
the wrong
one's...
way around.
That one's 0.4.
Yeah.
So what's the other one then?
The other one's 0.8 and 0.2.
I did not see that. Hang on. 0.8. And I think maybe we'll just add in something like we'll say first and second.
Yeah.
Something like that. You know, just so that's the first, that's the second. Okay. Part B.
So for this, would you do 0.7 times 0.8?
There's a simpler way.
Oh, you check if the two numbers are the same, and they're not the same, so they're not independent.
Yeah, 0.8 not equal to 0.4. Therefore, they're not independent. Yeah, however you would say it.
Yeah.
And see. You'll be on only one hole. Okay, how do we do this?
So for this, would you do 0.3 times 0.6 add 0.7 times 0.2?
0.3. So what was it? 0.3 times
0.6.
So that would be he doesn't get either of them, wouldn't it? We wanted on only one.
Oh yeah. So it'd be 0.3 and 0.4.
Yeah.
You multiply them, and then you add it to, and then 0.7 times 0.2.
Correct.
Which gives you 0.26.
Sounds good. 0.26, yeah, we got the idea there. Let's see this one. An experiment 3 times. So that would be 3 branches, I think. All 3 rows are odd. So let's do it without tree diagram. What would be part A?
Would you do 0.6 times 3?
Let's see. So that would be... No, it would be 0.6 times 0.6 times 0.6.
Okay. which is 0.216.
Not 0.216. What's a short way of writing 0.6 times itself 3 times?
0.6 cubed.
Yeah, so it's to the power of 3, not times 3. What is 0.6 times 3?
0.6 times 3 is 1.8.
What do you know about probabilities?
Can't be off 1.
Yeah, and so that would be, you should, like, if you type that in, notice that that's more than 1. So I've gone wrong somewhere. Something's not right. B, what we'll be doing in the next chapter. So if you do a tree diagram, oh, I don't have one. If you do a tree diagram, just one of 3 rows is odd. So let's say you get odd, even, even.
Yeah.
But there's lots of possibilities. There's also like even, odd, even. Oh, is that it? And then there's what? Even, odd.
Even, odd. Yeah.
There's only 3 possibilities, I suppose. And so this one would be 0.6 is this, just one of them is odd, so that's to the power of 1.
Yeah.
Then 0.4 to the power of 2.
Okay. Yeah, because that's the first roll, the other one's the second roll, right?
Yeah, so that's like that, but then you times it by 3 because there's 3 of these things.
Okay.
So try that. I want to see what it says.
Okay.
Yeah.
I got 0.288.
And that's what it's supposed to be. This reminds us of our binomial expansion. 3 choose 1, 0.6 to the 1, 0.4 to the 2. That's what that is.
Yeah.
And 3 choose 1. Anything choose 1 is itself. And so 3 choose 1 is 3. And so it's just those 2 and then times 3, which is what we had.
Yeah.
The experiment is repeated twice more. Find the probability of obtaining either 3 odd numbers or 3 even numbers all 3 times. Hang on. The experiment is repeated twice more. So they do the experiment 3 times. Holy God. So then this is probably easier with binomial.
So would you do 0.6 cubed times 3?
No, I believe you would do 0.216 cubed.
Okay.
I believe that's what you would do because the probability, so it's basically the probability of 3 odd numbers is like the answer to part A. So that would be 0.216 to the power of 3. Or 3 even numbers all 3 times. What's the probability of an even number 3 times?
0.4 cubed.
I believe, so in this case it would have to be 0.4 cubed and then cube that. I think that's what it is it?
Yeah, I think so.
Right, I just want to check if this is right.
I got 0.01.
Exactly 0.01?
No, 0.010333984.
Why would you get my hopes up like that? Okay, let's see. Did I do something different than you?
I put the cube in the bracket. Yeah.
I forgot one. Alright. Okay. Answer. It's just given. Alright. Let's see. 3, 4, 3 over. Hmm. 0.02. Alright. We'd have to do the tree diagram. Let's not. And it's probably easier with binomial expansion. So let's not worry about that.
Yeah.
I just don't want to bother with, tree diagrams. You're okay with them. Let's see, draw a tree diagram to represent this. It's tossed 3 times, and I just know that in the next... Alright, what's part B for this one?
Okay. Would this be a third cubed?
Yeah. What
Which is 1. No. A third cubed. One over 27, which is 0.4, rounded to 2 decimal places.
I like 1 over 27. Nothing wrong with that. C.
So for this, would it be, you'd need the probability for tails, which is 2 over 3.
Yep.
So for this, would you need to do a third times 2 over 3 times 2 over 3?
Yeah. But there's 3 different arrangements for it.
And then you multiply it by 3.
Yeah, you multiply it by 3, choose 1 basically, which is 3. Yep. And then D is this similar one again. Okay, the whole experiment is repeated for a second trial. Find the probability of obtaining either 3 heads or 3 tails in both. So how do you get the probability of obtaining 3 heads in both?
You do 1 over 27 cubed.
There are 2 experiments.
Squared then.
Yeah, so that's 1 over 27 squared. So you either get 3 heads in both, or you get 3 tails in both. And so my thinking, which we got wrong last time, is that this would be 3 tails, would be 2 over 3 cubed, which is the other part, kind of the other side of part A, and then that answer squared. I just want to see, do we have working out? So why did I always simplify it? So 1 over 27. This one was 4, 8, 12 over 27. That is going to be 3. 3s are 9. 27. 6 over 20. 1 head only. Okay, so we're doing this a very long way. So then heads, heads, heads are tails, tails, tails. I see our mistake. I think it's Bidmas is our mistake.
Okay.
We need to do, so the probability, this is what we need to do. We have to do that. That's it.
Okay.
And so let's just see if that works for this one. So it is like that, I believe.
Okay.
Let's just try it in the calculator. 6 cubed.
I got 4.07 times 10 to, yeah.
3, 4, 3 was not that. I don't know. Alright. One way you can do it is you can just do it like this. Just a long way.
Okay.
Just don't want to do it the long way.
Yeah.
And this is how you're supposed to do it.
Yeah.
Just don't want to. Okay. another tree diagram except with percentages. Yeah, fine. A bag containing 13. Yeah, right. How about this one?
Okay. So for this, it would be out of 26.
Yep.
So it'd be, for the first one, it'd be 6 out of 26 times 5 over 25.
Yeah. How about B?
Four over 24.
Yeah, so it's basically just that times 4 over 24.
Yeah.
25, then there's 4 over 24. And then find the row that all three tokens are different colors. It's just long.
Yeah.
Okay, this thing, filling in the blanks isn't too bad. So yeah, let's try filling in the blanks for the diagram.
So just from looking at it, you could say that from green to blue in the top, it would be, the blue would be 3 over 5.
Yeah. And you just do that for the rest of it?
Yeah.
Hence write down. So Q, 2 balls, same color. When the ball is blue. I think you're okay for tree diagrams. It's like extra GCSE.
Yeah.
So that one?
Tick.
Yeah, don't worry about this tree diagram stuff. Right. This is the stuff that we need to do. Okay, let's do it. Statistical distributions.
Okay. So if this would be all the possible outcomes, so it would be, because one coin has 2 outcomes, all coins have 2 outcomes, so it would be 2 times 6 times 3.
Part A. All possible outcomes. So one
If you
is...
said like one could be like heads, or it could be heads or tails.
So heads.
There'd be heads. There could be heads and tails, tails and heads. Heads, tails, tails.
So I'll put that last.
Okay. There could be head, tail. Head, tail.
I'll go with head, tail, head.
And then you could have tail, head.
Put that second last.
And then heads, tails.
Tail. Did we do tail, head? So there'll be tail, head.
And then tail, head, tail.
Then tail, head, tail. I have to put at the end, unfortunately.
Yeah.
So that's 1, 2, 3, 4,
8.
5, 6, 7, 8. So I think it's like 2 to power 3. 2 possibilities. 3. Yeah. Let me see. Head. Yep. Okay. B. Any idea what that's about?
No.
As a table, you have x.
Yep.
X can take, what is it, the possible, is defined as the number of heads when the 3 coins are tossed. So what are the possible values for x?
But there are like no values to when tossing a coin.
Like the number, it says x is the number of heads. The number of times it lands on
it's
heads.
3.
All right, one possibility is 3. Another?
2.
Yep.
Another's 1, and another one 0.
So let's do that. 0, 1, 2, and 3. The other part of the table is the probability of like this particular x being this one. What is the probability of 0 heads?
0.
How many out of how many have no heads?
1 out of 8.
Yep. And 1 head.
2 out of 8.
Count again. 1 head.
Of just 1, or can it be more than 1?
Just 1. Exactly 1.
Okay. 3.
Yep. Exactly 2 heads.
2.
Count again. That's 2. 2.
Oh, it's 3. And then 3 heads is 1.
That one's 1 out of 8. Great. As a probability mass function. So let's see if I remember how this thing goes. The probability that x equals x, I think it's something like that. And then you have this thing. Oh, I never remember which way they go. So they can be 0 or 3. Has a probability of an eighth. 1 or 2 has a probability of 3/8. And then otherwise, probability is 0. It's nothing else.
Okay.
And it's, let me make sure on that one. So probably, so x equals, wait, where's x equals? Oh, it's the other way around. I always get it wrong. Okay, the probabilities go in there. It seems like it would make sense the other way around.
Yeah.
So that's 1 out of 8. That one's 3 out of 8. And that one's 0. X equals 0 or 3. So you can see how it compresses it down a bit. You don't have 1/8 twice or 3/8 twice. And yeah, let's see. Okay, fine. We get the idea. Right. How about this?
Okay. So it says from above 1 and equal to 3. Does that mean 2 and 3, which is a half and an eighth?
Yep. What's a half and an eighth?
Put together, like added.
Yep.
5 over 8.
That's great. Next one.
So x is above 2. So would it be an eighth?
Above 2, that's less than 2.
Oh. So it'd be a quarter add an eighth.
Yep.
Which is 3 over 8.
Mm-hmm.
And then is that above 3? So would that be 0?
Yep. 0. Okay. A random number generator from 1 to 20. Oh, this one. Let me see something. Maybe I'm wrong about this. This is 1.1. 1.1. Alright. Given that x is the random variable, the name of the distribution of x, if every value is equally valid, it's called uniform.
Okay.
Yeah. So it's called discrete uniform distribution. Yeah, but important thing is uniform.
Yeah.
Okay. Let's see. So this is equally valid. But no, it's not the best question. Let's get rid of that. Okay, how do we do part A?
Okay. So we're trying to work out alpha.
Mm-hmm.
So with that, so for 3 it says just A, well alpha.
Right.
And we know that the random variable is equal to y, which is the numbers at the top.
What do probabilities add up to?
1.
You can use that.
So would it be, you could use alpha equals 1 then? Oh no, alpha would be, you could just do alpha plus a sixth equals 1.
No. Alpha plus a sixth plus alpha minus an eighth plus alpha plus 2 alpha. What must that give you?
Equals 1.
Yeah, they all add up to 1.
Okay. And then for this, would you need to, could you just add all the alphas together?
Yeah, I mean, you can also just, you know,
Sub it for x.
x plus
I got 0.2.
like that, is it?
Yeah.
And let me just press answer. So it's 23 over 120. I like that better. And how could you do part B?
Would you sub in 23 over whatever it was in for alpha?
Yes. I think it was 23 over 120.
Okay. So it'd be 23 over 120 minus 1/8. Which is 1/15. And then you'd add alpha again.
Yep.
Which gives you 31 over 120.
Yeah. So I just did answer minus an eighth plus answer. Yeah, it's basically, yeah, alpha minus an eighth plus alpha. Great. Okay. So the probabilities add up to 1.
Yeah.
Let's not forget it. Okay. This one. Yep. Let's do it. Part A. Any idea how this thing works?
No.
So there's a quick way, but we'll just kind of make sense of it.
Yeah.
So if we had the table, it's 1, 2, 3, 4. They say the possibilities are.
Yep.
And they say it is k over x. In the first box, what is k over x? When x is 1.
Well, so when x is 1,
It's k over 1.
Okay.
Second
So it'd
part.
be k over 2.
Yep.
Then k over 3 and then k over 4.
Yep. Find the value of k.
So we know all of it adds up to 1.
Yep.
So we could do x over 1 in the calculator.
Yep.
Add x over 2.
Mm-hmm.
Add x over 3. Add x over 4 equals 1, and then shift solve. And you get x is 0.48 or 12 over 25.
I like 0.48. Okay. And so that's k. And so complete the table.
Okay. So you do k over 1.
What's k?
So it's 0.48.
Yeah.
And then k over 2 is 0.24.
Mm-hmm.
And then k over 3 is 0.16. And k over 4 is 0.12.
That's it. And then part C.
Okay. So is that greater than 2? So it would be... Is it greater than 2?
Yep.
So it'd be 0.16 add 0.12.
Yep.
Which is 0.28.
Yeah, so that one is 0.28. And what is the last one?
0.
Correct. So 0.16 plus 0.12. That's what we'll use to check. So they did it as fractions. All right. 7 over 25 is 7, 14, 28, 0.28. Yep. Great. They did. So it's like, let's make sense of this because it's a bit weird. So you start off just the raw data, head, tail, that type of thing. You boil that down to how many times can it land on heads? 0, once, twice, or 3 times. Here's the probabilities. You have 1/8 twice, you have 3/8 twice. And so you can boil it down to be a bit smaller. So you don't repeat 1 over 8 and 3 over 8. You boil that down even further and you create, it's like a formula for creating one of these tables. K over X. So whatever, and that K turned out to be 0.48. So it would be like 0.48 over whatever X is. We'll give you its probability.
Right. Yeah.
All right. Let's try it.
So for this, we do 1x. Well, it will be in the calculator as 1x, add 2x, add 3x, add 4x equals 1.
Mm-hmm. Well, no, equals 1. Not calculator, because it's a show that question. They told you the answer.
Oh, so then you do... So it'd be 10x equals 1.
Yep.
Oh, you say 10k really. It wouldn't be 10.
Sorry, you're right. 10k equals 1.
Yeah.
Yeah, so we're thinking that calculator. 10k equals 1.
Yeah.
And then you can
say... divide by 10 on both sides.
Yeah, and then you can say k is 1 over 10.
Yeah.
And I'll write there 4 before. So we have to show that. Great. Let's see this one. It's very similar. Let me see this. Yeah, that's very similar. I think you're good. Let's see, this one's a bit weird. So explain does not describe a probability function. I think if you sub in her values, you'll probably get more than one.
Yeah.
Part B. That's very similar. It's just k over 2 squared plus k over 3 squared plus k over 4 squared equals 1. And you go from there. The sum of probabilities is not 1. Ah, okay. So hers wasn't bigger than 1. It just wasn't 1. Okay. So it turns out, so she said it was 2. It was actually 2 and close to 2 and a third.
Yeah.
Right. Let's give this a go. This time we've got 2 functions. What's this about?
So for this, would you need to use 2 and 4 for kx, or is 2 and 4 only for k brackets x minus 1?
2 and 4 is for only that one.
Okay.
1 and 3 is only that one.
Okay. So would you sub in 1, so it'd be k add 3k equals... Would it not equal 1, or would it equal 1?
We have other stuff. X can also be 2 and 4.
So could you do add 2k?
Sub in 2 for x, what do you get?
K and then 2 minus 1.
Yeah.
Which is 3k.
That's 2 plus 1.
Oh, just k then.
Yeah.
The other one's 3k.
Yeah, well done.
Equals 1.
Uh-huh.
Added together, that gives you 8k. You divide by a on both sides, which gives you 1/8.
Great. And then, okay, what is the probability that it's greater than 1?
There's 0.
No. That x is greater than 1. Not probability or anything.
Oh. It's greater than 1. Is it 3/4?
No. So sub in k for these values.
Oh.
So let's say it's
To be an eighth times 1, which is an eighth.
So what is the probability of getting an x being more than 1? Yeah, so the probability of a 1 is an eighth. And so what's the probability of more than 1? Well, it's basically probability of 2 or 3 or 4.
So would it just be 3/8?
All right. So sub in what you need.
So it'd be an eighth times 3.
Yep.
Which is 3/8.
Yep. Come on.
And then you do 2 minus 1, which is 1. 1 times an eighth, which is an eighth. Then 4 minus 1, which is 3 times an eighth, which is 3/8.
What do you get?
And altogether you get 7/8.
That's it. And so the probability of 1 is 1/8, and so the probability of not 1 is 7/8.
Okay.
And that's a quick way. Instead of having to work out these 3, you can just do 1 minus this 1. And it's just a quick way of doing it. Okay. Oh, it's a duplicate. I can get rid of that. Yeah. Okay. Very strange one. How about this?
Okay. So for this, would you need to substitute 1 for 5 minus r,
Well done.
which gives you 4.
So the probability, well, let's say we sub in 1 for r, yeah?
Yeah.
So the probability that x is equal to 1 is equal to the probability that x is equal to 4.
Yeah.
What's
And the
next?
other one would be 3. X is equal to 2. Probability of x is equal to 2.
So the
Equal
probability
to
x equals
probability. Yeah.
yeah.
Equals 3.
Okay, what's next?
So it gives us that the probability of x being 1 is 0.28.
Yeah.
So we know that x equals 4. Would that be 0.28?
Well done.
Does that mean when x is 2, is it times by 2?
That means, well, they wanted it as a table, so let's do it as a table. How could you put it in as a table? What we have so far?
Would you have x equals r?
So we'd have x
And then r in the top.
probability. Oh, sorry, it's r. Yeah, r and the probability x equals r. Okay. All right. So what goes where?
So you have 1 in the top and then 2 after that. And then when you go up to 4, 3 and then 4.
Yep.
And then for the first, and then it'd just be 1, 2, 3, 4 for everyone.
Probability.
Oh, for the first one it's 0.28 then.
So for 1 it's 0.28.
So how do you work out 2, 3 and 4?
We already know 4.
One.
You tell me the probability x equals 1 is the same as the probability x equals 4. So if the probability that x equals 1 is 0.28, what's the probability that x equals 4?
Zero 0.28.
Yep, you told me that earlier. Okay, we also know the probability that x equals 2 is equal to the probability x equals 3. Those two are the same.
So that means you just add them together, minus from 1 and then divide it by 2.
Yep.
So you get 0.56 minus from 1 is 0.44 divided by 2 is 0.22.
Yep. 0.22, 0.22. Let's see this one. Part B, the dice is rolled twice and the totals are added together. Find the probability the total is 7 or more. Okay. So how would you do that? 7 or more.
Okay. So for this, would you need to work out like every combination of dice to see which one's above 7?
Yeah. So successful outcomes. And it can only land on 1, 2, 3, or 4.
Okay.
So what plus what will give us 7 or more?
4 plus 3.
4 and 3. Any other possibility?
3 and 4.
Is that it?
Uh, 4 and 4.
Yeah, because it says or more.
And then could you do 4 and 4 again? Is that not? Does it not work like that?
No, because it's exactly the same thing.
Okay.
Okay, and so how about this?
So would you add them all together?
Right, and what?
So you'd add 4 and 3, which gives you 7.
No, probability of 4 or 3. So probability of 4.
Is 1 over 4. Oh, it's not 0.28.
Yep.
And then add, which is 3, which would be 0.22.
Times probability
Okay.
of 4 and 3. The or is the adding.
Okay. And then you do 0.3 or 3 again, which would be 0.22. Add 0.28.
We want 3 and 4.
Oh, times it.
Yep.
And then you do 0.28 squared.
Yep. Well done.
You worked it out.
Let's try that. Can make sure it's right.
And you get 126 over 625.
SD, is it 0.2016?
Yeah.
Great. Got it. Okay, so this one's very difficult, but yeah. So it's now it's still the same idea. It's a formula to give you the probabilities given the x,
Yeah.
and yeah. So this is from the review exercise. That's all right. Yay! Okay, we made it. And so that stuff. What do you give yourself?
Probably between a tick and a half.
Yeah. See, now we're getting to the real stuff. This is good stuff. Yeah. How was that for you, Adam?
That was good.
And so continue this next time.
Yeah.
Any questions for me in general?
No.
All right. Well done, Adam. You did great.
Thank you.
I look forward to chatting again next time.
You too. Bye.